and we'll jump into it here. So yeah, just a brief overview. This is basically split into two parts. I want to talk about zero field, solid state, nuclear quadrupole resonance, and then I'll finish up by talking about Earth's field NMR that we use in solution state. So before getting into everything, I figured it'd be good to shout out some of the other sort of low field reference material, particularly what's been done on these other global NMR meetings. So John Blanchard, who's done a lot in this so-called ZULF NMR, gave an excellent tutorial. There's been meetings on hyperpolarization with the ZULF, also a really nice talk on sort of combining low field and high field. I'll try to reference several review articles and book chapters throughout, but again, John Blanchard with a really excellent review article on ZULF. Megan Hulse and Paul Callahan have done a lot of work in Earth's field NMR, so you can find I think a couple book chapters from them, and yeah, more to come on that. So I figured it'd be good to just sort of give some context as to why we're using these spectroscopies at Los Alamos, and really why I'm here today. So I was funded by this team at LANL to try to answer this question: if we can use something like magnetic resonance to develop some detection tools or something like a package scanner to try to stop the spread of fentanyl into this country. So the lab's taken a very serious investment, well over $5 million over 3 years, a lot of people involved. And the reason the lab's taken such a serious investment is just the severity of the problem. So really, we're looking at one of the first major declines in U.S. life expectancy in recent memory. And even looking at more recent data, you can see the sort of steep downtick uniquely in America. Now, of course, there was a global health crisis in 2020, but even regardless of that, we're approaching this situation where we're nearly hitting about 100,000 deaths a year in total opioid deaths in the United States. So really staggering numbers. The reason it's so lethal, this fentanyl or synthetic opioids, just 2 milligrams of fentanyl pictured here is a lethal dose for an average adult. Now you picture that to maybe previous epidemics of heroin, their lethal doses pictured there. Even compare that to other forms of fentanyl, something like carfentanil, it's 100 times more lethal than just fentanyl. So, a really lethal, serious problem. And again, want to try to develop some meaningful detection tool to try to stop the influx of the country. So again, we want to use something like magnetic resonance. I think it's worth looking at sort of what is the state of the art of high field, and what does the field look like, and also sort of brief background on myself. This is me pictured in Rob Sherko's group, my PhD advisor. And here we are at the Tallahassee Magnet Lab, shortly after we moved to Florida, and we're pictured in front of their flagship instrument, the Series Connected Hybrid. So it's a 36 Tesla magnet, strongest field to do NMR in the world. That gives you 1.5 gigahertz for proton NMR. And, in some sense, this is the goalpost or a sign of the times, right? Brooker's now sold more than 14 of these gigahertz class systems. And, this is pretty serious investment if you're going to go this route. We're talking about a $10 million instrument or more, really serious upkeep in terms of the cryogens, the highly trained staff. Even the infrastructure requirement is pretty serious. And I think it's just worth noting, the reason we're going to this gigahertz class really is resolution. I don't know that SNR is really a problem at 9 and 14 Tesla and what have you. Really, we're talking about resolution. So to offer the sort of alternative perspective, again, in this review article from John Blanchard, here he's describing, the, let's say, average low field NMR instrument. So you might have your sort of main magnetic field for detection, your RF shielding. You have your, spectrometer, maybe your tuned circuit, your RF amplifiers, and, look at this. It all fits on a cart, a few feet tall. It's on wheels. That's, it's portable. There's no cryogens. You just need to plug this into your power source and away you go. Such low fields, you can have untrained staff getting close to this instrument. The wrenches are going to fly off their tool belt. And a more extreme example where we're ultimately interested, this sort of NQR device. This is from my advisor, Michael Malone. You can see he has the main sort of detection coil, his tuned circuit, all in a small RF enclosure. Again, just plug this into an amp and a power supply and away you go. So, as someone who might be a PI soon, I like the sort of possibilities afforded by, this accessible, DIY, inexpensive route, rather than where the field seems to be heading as a whole. So, it does beg the question too, why such high fields? Again, I mentioned resolution. So A really classic example of this, it's been shown many times in the solid state NMR context. Here we're looking at aluminum 27 NMR. This is of this aluminoborate complex. And we can see even a very high field of 14 Tesla, this is not enough resolution to really figure out what's going on in your analyte. We cannot figure out, the number of sites and the tensor parameters from this alone. Really, you have to go to higher and higher field where you ultimately hit this regime, which is, quite nice. You're basically just having one peak per aluminum site. And at the end of the day, this is what everybody in NMR would like to measure, this very high resolution, sort of straightforward spectrum. Really, if we were developing an aluminum detector, this would be the kind of spectra we'd want, right? So more so towards thinking about fentanyl and this detection, recognize these are solids at room temperature. So we're not going to do proton NMR, right? The dipolar coupling is very low resolution. Carbon and oxygen, extremely low abundant. 14N starts to become pretty interesting, right? That basically 100% abundant. Now, in the context of high field, 14N solid state NMR, there's no resolution gain to go into these higher and higher fields. If you haven't seen this before, this is basically your average 14N powder pattern spectrum. It's spanning nearly 2 megahertz in this case. So again, if folks haven't seen this before, if I draw this sort of band here, that band's going to represent, say, my entire proton chemical shift range, carbon chemical shift range. Really, most chemical shift ranges in hertz would fit in that box. So we're talking about really an insanely broad spectrum. So inherently quite low in resolution. And again, this is a single nitrogen site in a sort of average small molecule. So to show where this kind of really falls apart, if you were to have multiple nitrogen sites like this compound melamine, there's 6 nitrogen sites that are inequivalent. And what we're showing here is a simulation of the sort of best guess of those individual inequivalent sites overlapped. And then what we get is in experiments is in black. So, you tell me in the audience, you measure the spectrum in black, how many nitrogen sites do I have? What are their tensor parameters? This is a, pretty difficult task from this data. So instead of the, high field solid state NMR, we want to think about using this zero field nuclear quadrupole resonance. So to offer my sort of hand wavy explanation of how this is working, trying to draw this analogy here and referencing this really good book chapter from Brian Suits here. So to think about first the NMR case, we're talking about, we have these nuclear dipole moments that will align either with the magnetic field or against the magnetic field, right? So some low energy conformation than the high energy conformation, slightly more in the low energy, and that gives us thermal polarization. And we're sort of asking the question, what energy is required to reorient those nuclear dipole moments in B naught? Now, in the NQR case, this is only working on quadrupolar nuclei, so spins greater than 1/2. We have these non-spherical nuclei, and now they're sensitive to something called the electric field gradient. So in a similar enough manner, there will be a low energy conformation of the quadrupolar nucleus in the EFG. There'll also be that higher energy conformation. And it's really the same question, what energy is required to reorient that nuclear quadrupole moment, now in this case in the EFG rather than the B naught. So this is just to say it's similar enough in terms of, we use the same language. There's still a T1 and a T2 here. There's pi over 2 pi pulses, echoes, all the rest of it. So if you know enough about this, you can probably already get started in NQR. And before getting more into this, I also want to reference some really good examples and review articles. So David Bryce and Pat Zell have this really excellent review article. Bryce has been doing excellent NQR work for more than 20 years now, I believe. And here, this is a great example showing he has 2 inequivalent chlorine sites in this compound. Here he has the high field solid state NMR for chlorine. Again, these really broad powder spectra. They can, in fact, resolve the 2 sites, though, I'll note this is potentially a time-consuming experiment. You also have to be a little careful to actually, ultimately resolve that. But I believe using the same probe, just pulling it out of the magnet, doing the zero field NQR, you can see this really nice regime, right? You just get 1 peak per site. Again, something like what most spectroscopists are looking for. And you can still characterize the tensors from this, perhaps with Zeeman perturbed NQR, even just from nutation experiments. Another book chapter from Pat Zell and Stephen Wren talking how NQR is used in pharmaceuticals. So a lot going on in sort of material science. And then a recent review article from Sumanjit Mandel talking about NQR used for substance detection and these illicit materials, more like what we'll get into here. So yeah, what's really interesting about NQR, basically we're getting the best possible resolution for measuring the EFG tensor, which is kind of ironic when talking about these high fields. Part of the reason for this, right? There's no orientation of crystallites to the magnetic field because there is no magnetic field. So now you're just left with these narrow lines. In the case of 14N, it's a spin 1 nucleus. So we have these 3 energy levels. We actually observe 3 transition frequencies, so highest to lowest. So if I simulate some, say, average 14N tensor parameters with the quadrupolar coupling and this asymmetry parameter, I'm going to see 3 of these lines for a single site. Now, revisiting our friend Melamine here, right, I mentioned this is sort of a problem at high field. There's these 6 inequivalent nitrogens. If instead we do the zero field NQR, here we're going to expect 6, there's 6 sites, so there's going to be 18 NQR lines in total. And we actually resolve about 15 of them quite readily. Some of them get to be pretty low in frequency, so the SNR takes a big hit. But nonetheless, this is sufficient information to do individual site identification, get the tensors. And, again, this is something more like what most NMR spectroscopists are used to, this sort of higher resolution spectrum, if you will, more like what we want in the detection context. Now, I'm sure some of you are familiar, the challenges associated with NQR are many. Signal sensitivity, incredibly weak, no magnetic field, relying just on the quadrupolar interaction, which is relatively weaker for 14N. So we get around this with the usual tricks, large sample volumes, long experimental times. We do have this extreme problem, certainly in 14N of like small organics. The T2 could be really short. It could be the limiting factor on T2 star. If that's less than your dead time, you're never even going to see signal. And what I want to talk about a lot today is this sort of search for signal, if you will. So another example of high field powder spectrum. In this case, this is urea. This is about 4 megahertz broad. And I suppose what's interesting about this, we know the 14N LARMR frequency. So we know to tune our probe here. And if you were to measure for long enough, you probably will eventually see some blob in the middle. And then really it's just a matter of if you perhaps sweep the field or sweep the frequency, you could actually trace out this powder spectrum. Now compare this to the NQR lines for urea, the same compound. Again, we have this really high resolution, so these really precise frequency locations, but the SNR is quite low. So, this is like a really extreme sort of needle in a haystack problem. If I'm some tens of kilohertz away from the suspected resonance, I'm just not going to see it. And really, this is the main point. Without any a priori information, how am I going to go about finding these resonances, particularly in new compounds such as fentanyl? So really what we're recommending is this sort of generalized strategy that could hopefully be used for most materials. So it's always going to start the sample. In our case, we make fentanyl in-house. Then we can give the samples to crystallographers. They're able to grow single crystals, solve crystal structures for the first time, maybe identify polymorphs in some cases. Once you have those structures, you should certainly predict your EFGs with DFT when possible. Once you have that prediction, hopefully that's going to accelerate the solid state NMR measurements, which we will use here to try to sort of approximate the NQR frequencies. And we'll be using something called proton fast field cycling experiments, which perhaps some of you haven't seen before. And this is really nice because it tells us something about relaxation. And, it's really only at this point when we have all this information, do we feel it's appropriate to actually try NQR detection. And, really we want to try this, repeat this for any material, anyone out there, try this for a, small organic compound. But in our case, we're just working on different forms of fentanyl. So, one of these key materials that we're interested in is this fentanyl hydrochloride salt. We understand this is probably the most prevalent form of fentanyl that is found on the street. So, our team was able to make the sample and again, solve crystal structures. And this is the first reported crystal structure, just showing a single molecule here. Now that we have that brand new CIF file, we can hand that over to our DFT team. And, they'll do a couple things for us. Of course, they're going to predict tensors for the different sites, but also, do some site assignment, right? We understand this is the piperidine nitrogen, this is the aniline. And of course, you can get the chlorine since it's an HCl salt. Now that we have these EFG tensors predicted, we can hand these numbers over to Harris Mason, who's running our solid state NMR Los Alamos. And if you haven't seen these experiments before, we talked about how broad these spectra are. Notice they're totally symmetric, so you don't need to acquire the whole thing. And what's more, you don't even need to acquire this whole half. You really just need to focus in on these sort of key discontinuities. That's enough to characterize the tensor. So because of the DFT, Harris knows where to tune his probe ahead of time, and this really speeds up the experimental times. So sort of zooming in on those pieces, you can see the sort of refined tensors that we get from experiment. And likewise, we do the central transition chlorine 35 NMR. And, just a note, these are all static. We don't want to spin fentanyl, risk a rotor crash, and, there's also no benefit to spinning in this case. So I think something interesting we stumbled upon here in looking at these tensors, in particular, if we're looking at this aniline nitrogen site, what I'm showing you here is the experimental curve in black, and then I have 3 simulations. So I'm simulating the same tensor in each case. And in green, I have the Simpson simulation using first order perturbation theory. And then I can actually take Simpson up to third order perturbation. And then ultimately, really what we want to do is use exact simulations like in Quest from Fred Perron and David Bryce. And, just to show sort of discrepancies here, if I was actually to fit just in first order and then, get the best fit from the exact simulation, this is a pretty significant discrepancy in the tensors. So just at first order, I would have missed the experimental NQR lines by about 100 kilohertz. I never would have saw a signal. But because we use that exact simulation, we got the tensor a lot closer. We ultimately within just 10 kilohertz of the NQR search, and we basically saw a signal right away. So really significant thing to consider here when the CQ is getting this large, perhaps less significant for these smaller CQ nitrogen sites. Just a note, if you do this sort of frequency discontinuity fitting to solve for the tensors, this is again a first order approach. So this might fall apart for larger tensor values. And I hadn't seen this before, and I think it's part of the reason is, not that many people are measuring 14N, and certainly there's not that many reports for these larger CQs since, it can be experimentally challenging to measure. So that was a bit of information on the EFG tensor parameters. Now I want to talk about this fast field cycling experiment. So what we need is, in this case, we use some standard sample, which has lots of dipolar coupling between nitrogen and proton. We're going to put that sample in some magnetic field. And when it's at field, the Zeeman, the protons experience some, Zeeman energy splitting. Now, if I already ramp down the field, recognize that Zeeman splitting is also going to go down. And at some point, that energy level is going to match those NQR transition frequencies. So when that happens, we have level crossing. You can have polarization flow from proton to nitrogen. And ultimately, what we're going to do is encode some information from nitrogen in the protons. So the way we measure this is with this field cycle experiment. We're always going to ramp up to some pre-polarization field to give good polarization to the protons. We're going to ideally ramp down to an intermediate relaxation field. So we'll increment some relaxation delay, measure the T1, and then we always ramp back up to a detection field where we actually measure NMR. So to show an example of these data for ammonium nitrate, here I have the proton T1 measured as a function of this relaxation field reported in the proton Larmor frequency. So what's interesting here, we expect NQR lines at about 420 and 490 kilohertz, and you kind of see these features emerge in the proton T1s. So how we generally analyze this is to just fit this polynomial, excluding these features, take the difference, and now you have something like the Zeeman perturbed NQR spectrum. And what's really interesting is what we learn about relaxation. So to show another example of this, a lot of this fentanyl detection work started with Michael Malone and Mike Janicki a few years ago. And here in this first paper, they were looking at the pharmaceutical grade of fentanyl, which is fentanyl citrate. So something you might actually find in a hospital. Now, again, I'm showing you the proton T1 as a function of that relaxation field. And in this case, going from about 1 megahertz to 4.5 megahertz. Again, you see that steady increase, but there's these really clear features in this case. So again, the difference is something like the Zeeman perturbed NQR spectrum for the 14N. And what's really significant in this case, notice in the ammonium nitrate, the T1 essentially is augmented at these frequencies. In this case, the T1's reduced. So if we look at the sort of magnitude of the depth here, right, the actual value of this difference, the sort of maximum value is like 30 to 40 milliseconds. And that's telling us the absolute upper limit of what the NQR T1 and T2 could be. So in reality, it's going to be a lot less than that, but to at least set that bound, ultimately they didn't observe the 14N NQR signal, and it's probably because of rapid relaxation. Again, maybe T2 getting shorter than the dead time. So now looking at the present material, this fentanyl HCl, again, showing the proton T1, in this case below 0.5 megahertz up to about 4 megahertz. So, we can identify several features readily. At about 1 megahertz, this is likely the piperidine nitrogen. At 2.5, this is likely the chlorine 35. And these two bands are likely coming from the aniline nitrogen. And what I'm showing in this sort of black dash curve is a spinach simulation of the Zeeman perturbed NQR using the solid state NMR tensors just to see if there's general agreement, which we do generally see, which is nice. And what's more significant here is in this region that we ultimately care about, the proton T1 is like 1 to 2 seconds. This is already much longer than fentanyl citrate. Again, the magnitude of this difference on the order of, say, half a second. So, something like 10 times longer than fentanyl citrate. So already very confident that we're going to have a much better chance to really do the detection in this material. Now, before getting into the NQR experiments, I just want to go over, how we do these experiments here in our lab. So we're big fans of TechMag. We use, in this case, we're using their LAP NMR, so a really small form factor, really affordable spectrometer. We use Tomco RF amplifiers, again, pretty affordable, especially if you're working at low RF frequencies. The probe is, of course, as simple as it could possibly be, single resonance, nothing fancy here. And something interesting that we use is, for our passive transmit receive switch, lambda over 4 cable at these frequencies is going to be something like hundreds of meters. So we don't really want to use that. Instead, we can use this thing called the Pi network. This is really nice. It's just a lumped element circuit, totally passive. And it gives the exact same effect as the lambda over 4 cable, assuming you set these values to be sort of tuned for the resonance that you're working at. And just a note on the probe design we use. So we happen to have a CNC in-house, which is really nice because we can machine these custom form factor probes out of aluminum, and we can make, thick-walled aluminum RF shielding, or just get whatever form factor we want. So something closer to what we actually use is shown here. We have these different sort of chambers, our capacitors, our Pi network, ultimately our sort of detection area. And, these aluminum walls are, nearly 1/2 inch thick. So we got good RF shielding, but also it's just a really rigid mechanical system. And, you can mill in whatever RF adapters you want. And just to know, okay, everyone doesn't have a 5-axis CNC machine, but we did ask a machine shop, hey, how much would it cost you to, make this and sell us the aluminum box? And it's just about $2,000. So still a really simple, affordable solution here. All right, so come back to fentanyl HCl, right? We have a good idea of the likely NQR frequencies from solid state NMR. Fast field cycling gave us a sort of check on those frequencies. And fast field cycling also told us that T2 would probably be pretty long in this material. So, we tuned the box to 3.1 megahertz. We saw a signal, 3.3 megahertz saw the signal. And, we get pretty paranoid working in this low frequency world, make sure these aren't interference or what have you. So, sort of run through the gambit where we run a nutation. We see this expected NQR sort of damped oscillation. The NQR line should have a T1. We can measure that with saturation recovery. And in fact, in every case here, we're using CPMG to measure the signal. So again, it turns out the T2 effective is actually quite long. It's giving us a really nice SNR boost here, speed up the acquisition just at room temperature. So yeah, definitely very fortunate for the good relaxation times here. And just some more details on these characteristics. So, we actually measured higher resolution frequencies. We can do pulse acquire sequences, get the line widths and the T2 stars. Once we have these frequencies, just the two of the three, that's enough to solve for CQ and eta. And now we have what should really be the most accurate and the most precise determination of these EFG tensor parameters, since we're really only measuring that quadrupolar interaction and nothing else. Now, we ultimately tried to observe the piperidine nitrogen and the chlorine 35, but to no success. The frequency is taking a big hit here. We also understood from fast field from fast field cycling that the relaxation should be much faster for these two NQR sites. So, potentially not able to observe them within our dead time. But we're currently doing lower temperature experiments to see if that can help. And just a final note on this work. So, I had mentioned carfentanil, 100 times more lethal than just fentanyl. What was interesting here is that we actually couldn't form the single crystal, so we couldn't get a structure, so there's no DFT prediction. But we did run the proton FFC, and this was pretty interesting because, I see a couple features, I could fit this in spinach, and now I've actually already determined the EFG tensor parameters for probably the aniline, nitrogen, and carfentanil. So already a good start. But on the other hand, this is predicting pretty rapid relaxation. So again, might have to think about going to colder experiments. So yeah, that was what I wanted to say on this sort of NQR side. I'll just sort of quickly comment that, really, I suppose what I'm advocating for is, just trying to get as much information as possible. I'm not saying throw out the Brooker spectrometer, but, let's use everything together as much as possible for perhaps refining tensors and refining structures. Now we're at a point, this is pretty exciting. We have something that potentially could be quite useful, again, for the most prevalent form of fentanyl to actually have a, very simple, inexpensive, and portable package scanner. So now I'd like to switch over to this Earth's field NMR discussion. And, the general motivation here is the same question, can we use this sort of low field spectroscopy to do some meaningful detection work or characterization work for fentanyl? Now, before getting into any background, I think it's nice to just show why we'd want to use this, just sort of let the data speak for itself. It's a really nice paper from Stefan Apalt and Bernard Blumick, where if they're measuring, say, proton NMR of benzene at Earth's field, signal decaying well over 20, 30 seconds, a line width of just 34 millihertz. Similar story with lithium NMR, a line width of 17 millihertz. So really just amazing resolution. This is ultimately afforded by the fact that, this Earth's field or a zero field or most of these low fields, they're always going to be much more homogeneous than any 20, 30 plus Tesla magnet. Those high fields will just never get down to the homogeneity needed to achieve these line widths. What's more is, susceptibility broadening effects are extremely low here, right? So just as field goes down, susceptibility broadening will go down. So that's ultimately why we get these nice sharp lines. Now, if you're at Earth's field, you're no longer resolving chemical shifts. The ppm becomes just far too narrow in this case. So, but what you do measure is the field independent J coupling. So to show a very nice example from the same paper, this is the proton NMR of TMS, so the well-known shift standard. They're on a 9.4 Tesla magnet, good shims. This main singlet line has a line width of about 1.4 hertz. And now looking down in the baseline, of course, we'll see carbon satellites, but we'll also see silicon satellites in TMS. And in this case, the silicon J coupling is about 6.6 hertz, but you can see, even on this fancy system, we can't really resolve that coupling that well. Then compared to the Earth's field, which is the TMS spectrum shown in black, again, that singlet line is probably some tens of millihertz. The 6.6 coupling is readily observable, and we can measure it to a much higher precision. And even comparing this to other silicon-containing compounds, you can already see the potential to do some meaningful sample differentiation when you pair the really high resolution, with the J-coupled spectra. Another nice example of this resolution enhancement. This is from my colleague and predecessor, Derek Caseman. So here Derek has measured a couple samples, this difluorobenzene complex and trifluorobenzene. In each case, Derek is showing you the 9.4 Tesla high field, a benchtop 1.4 Tesla spectrum, and then ultimately the Earth's field NMR. So in this difluoro complex, at high field, the line width is, usually on the order of a hertz. We have this sort of weak coupling triplet, if you will. If you go down to benchtop, the line width starts to take a pretty big hit. This is a pretty inconvenient field regime for resolution. And then ultimately at Earthsfield, we have something like that triplet structure, but really strong coupling is active here. That means we have the full interaction Hamiltonian, and that just means we're going to see many more peaks. So what is nice about this, if you can fit this, fit your J couplings, you're ultimately going to get a much higher, again, higher precision determination of those J couplings, but now also access to the sign of the J coupling in just this 1D spectrum. And compare this to a case where now there's actually chemical shifts. You can see at benchtop, which is the sort of comparison in terms of price point, the resolution is really just not there. Whereas in Earthsfield, relying just on the J couplings, this is with the really high resolution, this is enough to fully characterize the system by way of J coupling. Again, access to the sign. And I leave this to the audience. You tell me which spectrum of these you would ultimately want to characterize your sample. So more in the background here, how this works. So if we're going to measure Earthsfield NMR, we have to recognize that we cannot measure homonuclear couplings alone. So if I dream up this weird simulation in the spin system, say I have these 3 protons with these J couplings, and I measure the Earthsfield NMR, I'm going to get a singlet. So I won't see anything. Really what we need is probably ideally an abundant heteronucleus to break the magnetic equivalence of these protons. And you can see that here. If I just introduce a single fluorine to just one of these spins, say some 10 hertz coupling, what I see is this sort of initial 10 hertz splitting, and then all the subsequent proton-proton homonuclear coupling is taken as a perturbation on that. So now we can characterize all the J couplings in the system. And what's nice at Earthsfield, we still have the Zeeman interaction, so we can also measure this effect on the 19F spins. Okay, so again, from the Appelt and Blumick article, they sort of explain what's happening in these heteronuclear systems as we go from basically 0 field to really high field. So some 2-spin species system. When we say high field, really we're talking about anything greater than about 1 millitesla, because we're almost always going to have weak coupling between heteronuclei just from the Zeeman interaction. I think what's kind of interesting that they point out, if you go too high in fields, you'll just basically never measure homonuclear couplings because your line widths will be too big. At the other end of the spectrum, we have this Zolf NMR 0 to ultra low field. If you're at 0 field, there's no longer a Zeeman splitting, just measuring the J coupling. Now, what's interesting, they sort of highlight this, what they call this most complex spectral region, which happens to be right around Earthsfield. So if we look at, again, simulating my sort of weird dreamt up spin system, if I simulate this at some high field, I'll assign some random chemical shifts for the protons, and we'll just ask the question, like, how many peaks are there? So in this case, there's about 14 peaks if you could resolve them. If you go to the 0 field, just measuring the J coupling, we basically end up with something like 12 peaks, could be 24 if you count it, symmetric. And then at Earthsfield, again, depends how you count it. If you take this sort of symmetric half, that would be 15. Really, this is 30 about the Larimar frequency. And then if you count the 19F spectra as well, that's a total of 50 peaks. So describing, the same spin system. So really the motivation is if we have this ultra high resolution and we have this really complicated spectrum, that should be a very good spectral fingerprint for illicit materials. Now, before getting more into our work, I just want to highlight some other interesting examples from other folks. So again, Megan Hulse, Paul Callahan have done a lot of great work in Earthsfield NMR. This was an interesting case. They actually did hyperpolarization by the way of Overhauser DMP. So in this case, they actually do the DMP at some millitesla field, and then they ramp back down to Earthsfield for detection. But you can see they get appreciable enhancements. Once they had their spins hyperpolarized, they actually did multi-nuclear 2D NMR. So because we get the proton and the fluorine in a single acquisition, if you just run 2D COSY, it's pretty crazy because you kind of get these 4 2D spectra, right? The homonuclear and the heteronuclear correlation. So really interesting stuff here. This is a sort of classic case. This is always fun to see and to describe. So this is from our friends down at ABQMR, just down the road in Albuquerque, New Mexico, Mark Conradi and Hilary Fabich. So some previous work they did. This is Earthsfield NMR as done from a helicopter. Basically, they partnered with an oil company to try to see, could they detect oil on the surface of a water? So they did this in a very controlled manner on a lake. But they basically have their coil set here, and power's running up to the helicopter, and this actually worked. They're able to measure the two different signals. And imaging is quite interesting at these fields. So this is an example from the Alex Pines lab of 66 microtesla. So what's interesting here is, when the RF frequency is just 2 kilohertz for the proton alarm frequency, there's really good RF penetration through metal. So you can see in an image of this pepper in a can, you can see there's no artifacts from the metal, and likewise we get a decent image because the RF is able to penetrate just fine. And more relevant to our work, this is a previous example of imaging at similar fields. This is the so-called MagVis project from Michelle Espy. And here they have basically a liquid bottle scanner. This was actually deployed at the Albuquerque airport back in 2008. And what they're showing here is a picture of different bottle samples. And here we have the proton MRI of the different liquid samples in bottles. And there's this sort of color coding that's just coming from a library of relaxation parameters. And the idea is, ultimately to try to do some threat detection based on relaxation, try to detect something like an explosive liquid. So more relevant to this sort of threat detection world and what we're doing here. So in terms of the sort of spectroscopy that we do at Los Alamos, again, the instrument developed by Derek Caseman and Bob Williams and others. If you're in a lab environment, Earth's field is not great. So, you have ferrous steel beams, rebar, all the rest of it. It becomes very distorted and inhomogeneous. If you're going to be indoors in a lab, you really want to apply the B naught of Earth's field using, just a resistive coil. So how this experiment works for us, we take a sample, which is quite nice. It's just a standard 5 millimeter NMR tube. The only sort of special thing is we tend to degas it, get rid of paramagnetic oxygen to keep the line width sharp. So we'll load this in this G10 rod, this fiber rod. That's being held by this motor, this linear actuator. And this is going to be very rapidly shuttled between this 1 Tesla magnet for prepolarization. So Earth's field, 50 microtesla is going to give you very poor thermal polarization. It's basically necessary to prepolarize. The motor rapidly shuttles it into this detection area where, again, we have our Helmholtz coil with B naught at Earth's field. We have a pretty simple 3-axis shim, which helps clean up the line shape. And we have this aluminum RF shield. We have the low Q saddle coil for excitation. We are doing inductive detection with this highly inductive solenoid. And we have just a home built spectrometer running on LabVIEW. And away you go. So to show a previous example of how this was used for detection, again, from Derek Caseman, this initial work was funded to see, could they use Earth's field NMR to do meaningful sample differentiation on chemical warfare agents? So we're talking about things like sarin gas, where you basically have this sort of central building block of this phosphate group. And what Derek's done here is he's used different functional groups on this main block, and he's just trying to see, is the J coupling between proton of those ligands and that phosphorus, is that going to change in every case? And, how sensitive are we to that? And you can see as he puts on many different sorts of ligands, you can see in every case we get a very unique Earth's field spectrum, and a very nice resolution. And, this is your sample differentiation and characterization. It's not really necessary to even have a chemical shift in this case if you're just trying to tell what's what, or, do the threat detection ultimately of something like sarin. Now, if we're thinking about detecting illicit materials in general, we got to recognize that nitrogen is almost always present in most of these materials. So if you're not familiar with this, if you have J coupling from proton to 1014, what you're going to see is a triplet because of the spin 114 nucleus. Now, what's pretty interesting, you have to consider the T1 of this 14N, which is given by this well-known quadrupolar relaxation. So thinking about the rate, inverse T1, that's going to be dependent on its quadrupolar coupling and its correlation time. So what John Popel showed back in the day was, as that relaxation rate increases, you're initially going to broaden your triplet. You'll eventually hit this regime where there's sort of coalescence of the 3 lines. And then ultimately, with really rapid relaxation, the nitrogen will basically decouple itself. So it's as if the nitrogen was never there. Now, these effects should be really important to consider because, for threat detection, right, explosives, warfare agents, drugs, there's almost always nitrogen. So, before this study, we weren't sure how these effects would manifest at Earth's field. So to sort of briefly touch on this, again, reference the publication if you're interested in this more. We have these two compounds, these fluoropyridines. We figured these would be decent surrogates of, more controlled substances. And what we're comparing here is this 3 and 2 fluoropyridine. So in this case, the J coupling from fluorine to nitrogen will, of course, be much stronger. And what I'm showing you is the proton signals and the fluorine signals. And what you can see in this case of the 2-fluoropyridine, right, the line broadening is very extreme, more like that coalescent regime I described. And what's actually kind of interesting about this, I have these sort of best fit simulations in each case. I have to include the 14N relaxation to be able to simulate this at all. And even sort of fitting these as a function of that relaxation rate, I've actually now measured the T1 of the 14N just from these 1D spectra, which was kind of cool. Now, what was unique about the Earth field NMR, I'm really not going to discuss this. This is a bit too much into the weeds. Again, just reference the paper, but there are unique effects that happen because there's strong coupling between our, hydrogen and fluorine and nitrogen. So basically what we saw was these really rapid relaxation rates, which probably won't show up in high field, did cause line broadening effects at Earth's field. So just to say that the Earth's field is going to be more sensitive to these quadrupolar relaxation effects than, when strong coupling is present than would happen otherwise. Okay, so to sort of get to the finish line here, we're curious about using Earth's field NMR for detecting opioids. So here, again, looking at this fentanyl compound, I told you we cannot observe just proton-proton coupling, which, there's plenty of here. 14N is an abundant heteronucleus, but I've sort of described how it only causes line broadening in the spectrum. So really what we want to do is recognize that there are lethal variants of fentanyl that are fluorinated. In particular, where this fluorine either shows up at the aniline ring or this phenethyl ring. There's even this other compound that's been suggested as a sort of less toxic painkiller where the fluorine's at the piperidine ring. But nonetheless, these should be suitable compounds to try the Earth's field NMR. So first looking in this case where the fluorine is on the piperidine ring, what I wanted to see here was if I take the starting reagent, the intermediate, and the final fentanyl, can I, let's assume that the J couplings are probably going to change, and then I should get a unique spectrum in every case. So what we're seeing sort of initially is because we have just this 2-bond J coupling from fluorine to hydrogen, that's about a 50 hertz coupling. That's what really gets the spectrum started. And then we see all the other couplings, sort of perturbations to that. I suppose looking at, in either of these cases, we do have to include the effects of that relaxing 14N nucleus. And then ultimately, when we got to the final fentanyl, this is kind of interesting for us. Clearly I'm not seeing any significant signals, not resolving anything. And this was interesting for us just in comparing the precursor and the fentanyl. Notice I'm actually adding an additional proton here, so it's already that much more complicated of a spectrum. And what's more, we have now 2 nitrogens with a 3-bond coupling to fluorine. So, 1 nitrogen being present causes significant line broadening, SNR reduction. 2 of them is even worse, plus the many spin complexity. So it's just kind of interesting and showing, pretty clear limitations of how far the spectroscopy could go. Now, ultimately looking at the more lethal type of fentanyl, so you could have the fluorine just at the aniline ring, this monofluorofentanyl. You could also have this difluorofentanyl, so the similar substitution here, but also having it at the phenethyl ring. In either case, I'm also looking at the starting reagent, this fluoroaniline or this fluorophenethyl. So in these cases, because it's a conjugated ring, now we're talking about a 3-bond coupling between hydrogen and fluorine. In this case, it's much smaller, just 10 hertz. And what I'll note is, there's no singlet peak here. That means all these spins are coupled and participating in the spectrum. Compare that to the fentanyls, there's many spins that aren't seeing fluorine. So that's why we have these really large singlet peaks. Now, in this case of this monofluorofentanyl, again, we still have this regime where there's this 3-bond coupling from fluorine to nitrogen that's ultimately causing quite a lot of line broadening here. We can just barely resolve that doublet. Compare that to this difluoro case where we do have that sort of line broaden aniline site, but now we have this fluorine, which isn't seeing any nitrogen, and that's giving us resolution to actually sort of resolve this sort of primitive doublet structure, if you will. Now, in both of these cases, there are many lines that are all overlapped, and you also consider the nitrogen relaxing here. But nonetheless, this is showing, even though the resolution's low, there is still this differentiation between potentially precursors and other types of fentanyl. Ultimately, the resolution's low here because of the spin system itself, not so much the instrument. I would say if the fluorine was at this 3 or 4 precision, you'd have significantly higher resolution in this case. So yeah, with that, I'll finish up. Just want to comment that this work was pretty cool to me, just because if you look at a lot of low field literature, there's sort of a lot of work on really small compounds, maybe on carbon labels, on alcohols, things like this. So looking at significantly larger compounds at natural abundance is kind of interesting. Certainly interesting for material science. About 30% of all pharmaceuticals are fluorinated anyway, and certainly lots of other coupling partners to consider. And yeah, with that, I just want to thank everybody who's involved with this work. Again, Derek Caseman, who taught me on the Earth Field NMR and started a lot of this work. Michael Malone, my postdoc mentor. Harris Mason, my co-mentor, and Michelle Espy was responsible for the fast field cycling NMR. Bob Williams, again, for Earth Field and for a lot of the sample prep. And yeah, I'm happy to take any questions.
Thank you, Adam, for the talk. We already have one question. From Benjamin. He said on slide 10, there was a 14N NQR simulation. He's asking, what software did you use to simulate the 14N NQR?
Yeah, in that case, I was using Spinach, so the MATLAB program developed by Ilya Kuprov. And I'll just note again that in the fast field cycling NMR, when I provide a simulation, that's actually doing Zeeman perturbed NQR simulations in Spinach as well.
Okay. I had one question regarding the spectra you show for the NQR or even for the health field. How much time does it take to acquire because you have a low field? So do you need multiple scans or a few scans is enough?
Yeah, so it just depends case by case. Ultimately in the NQR I showed, we did happen to have a lot of sample, which is helping the SNR a lot. Also, that long T2 and the CPMG helps, but we're talking about multi-gram scale. We can still measure in about less than a minute with that to get just a peak, but it really does take that kind of quantity, without sort of playing any other tricks. In the case of the Earth Field NMR, that's more like usually on the order of, let's say, a day or less for each spectrum. And part of that is, these are dissolved solids, right? A lot of these studies are usually on neat liquids. So, so we have, yeah, sort of dilution, but we also have, it does take a long time to measure. If you have high resolution and, you're going to measure for 10, 20 seconds. So even though I'm not taking that many scans, maybe 1,000, 2,000 scans, really just, trying to capture all that resolution is sort of taking a lot of time. So there are tricks you can maybe play there to, just speed up your acquisition time.
Okay. And just with following this question, have you ever thought of combining this with hyperpolarization?
Yeah, absolutely. Again, referencing what Megan Hulse has done with using DNP for Earthfield NMR. I think in that case, their enhancement was, sixfold compared to whatever their prepolarization field was. So I do like the idea of doing DNP since it's so simple, but there is sort of a little caveat there in terms of if you start doping in radicals, that's also going to broaden your line. So there's a trade-off there in terms of how much SNR you want to get against, resolution, as there always is. So.
Okay. Blake has a question for you. How long does the low field ramp relaxation spectra take to acquire?
The field cycling, I suppose. So yeah, any one of these experiments, we're talking about usually on the order of honestly weeks probably to get this. So something like this. Part of this is basically like a pseudo 3D experiment, right? You have the NMR detection, you have your relaxation delays, and then you have all that as a function of the relaxation field. So this ultimate and the signals are pretty dilute in general. So it is certainly very long. This could be sped up probably orders of magnitude if you just really know where to look. You're only sweeping these frequencies. I suppose in this case, we were sweeping quite a large bandwidth, probably unnecessarily to some extent, but clear room for improvement there.
Okay, thank you. Okay, I had one more question. Maybe for the fentanyl, if you focus on this application, do you see in the future a possible, like, really commercial tool that could be developed, or is there like, I mean, maybe 10 more years of hardware development to manage to get to this?
I mean, with a lot of it's really, if we're talking about specifically NQR and fentanyl, a lot of it's just sample dependent. So
Mm.
I think there's not much hardware limitation. These are very simple spectrometers, very inexpensive. If you have the right sample, you can get that acquisition in reasonable time. As far as, the other sort of tricks we play to enhance signal, this might be introducing a magnetic field to do cross polarization, or just going to lower temperature, like cryogenic temperatures will help a lot. So these are very simple additions that are already implemented at certainly a high field NMR, and would just be easier on our sort of benchtop devices. So I think part of it is just the sort of runaway commercialization of the Brooker instruments, and a lot of this hardware already exists and is ready to be used.
Nice. Okay. Okay, we have one more question from Thomas. Proton T1 dispersion normally show quadrupole dips, meaning shortening of proton T1 due to cross-relaxation via nitrogens. How do you explain proton T1 increase at nitrogen crossing?
Yeah, I mean, the dips are most often coming from just the fact that the NQR T1 is less than that of the proton. When it's increasing, that just simply means the NQR T1 is in fact longer than the proton T1, which is the case in ammonium nitrate. The proton T1 at these frequencies compared to that of the NQR. So if it is longer, it will be an augmentation rather than a dip, but the same mechanism.